University, China, as my teammate Gao Jianshun. It's our pleasure to report problem number 3, the Lego tower. This is the content of our report, including the following 6 parts. First, let's review the problem. A Lego mold, water and gelatin can be used to produce jelly or gummy Lego bricks. It is possible to build towers using these gummy Lego bricks in the same way as can be achieved with their plastic counterparts. What's the maximum height of gummy Lego tower that can be built, and how does this depend on the concentration of gelatin in the bricks? In this question, we only focus on the gelatin concentration for the height of the tower. Therefore, any analysis needs to be carried out under the same structure of the tower. Here we use the straight one. The next part is about our pre-experiment. First, let's analyze the problem in ideal situation. We envision that the gelatin bricks are exactly the same, with the same weight and shape, and it is rigid body, and it is a quasi-static process when we build the towers. Through this, we can estimate that the maximum height will be infinite. But in our pre-experiment, the result is that the height of the tower is about only 10 centimeters. So we must revise that 3 hypotheses in the ideal case. First, our method of making gelatin bricks can meet the first hypothesis. We will describe our method in the detail later. Then consider the second hypothesis. According to calculation, the deformation of the gelatin Lego bricks is extremely small, which can be ignored. It's not the reason of the collapse. So we conclude that the structure of the tower itself is stable. It's the external disturbance that caused the collapse. When the disturbance is within the allowable range of the tower will vibrate. Therefore, we use Bernoulli-Euler mode under the following 3 basic assumptions, and give the relationship between the tower's height and the ability of the tower to resist the disturbance. The left figure is the coordinate system we set up, and the right figure is the force analysis of the microelement dx. The oscillation of Bernoulli-Euler beam experiencing axial forces could be described as this function, with 4 boundary conditions here. When the axial forces is not 0, the equation has not an analytical solution. Here we use gelatin method to get a numerical approximate solution of the ith order inherent frequency. Using the approximate solution, we calculate that the amplitude of the first order natural frequency. Our final results are shown above. The bending moment on each point of the tower can be calculated with this equation. And we found the bending moment at the bottom is always the biggest during oscillation. Then comes the collapse condition. We reckon that the tower collapses when gravity torque and stick forces torque are smaller than the maximum bending moment, together with the fact that gravity is proportional to Lego brick density, and that sticky forces torque is inversely proportional to the deformation of the tower. We can finally have the collapse condition. This is the size of our gummy Lego bricks, as the same as the real one. Here shows the preparation of the gelatin solution. First, we weigh certain mass of gelatin. Then add certain mass of water. Here we show 20% concentration of gelatin as an example. Fully stirred in order to make gelatin mix well with water, then prepare to heat mixture with water bath in 60 centigrade. After 15 minutes, we observe that the mixture melts and turns to transparent and viscous. Finally, remove the foam which floats on the surface of the solution.
Remove it.
Then we can get the solution we need to produce our Lego bricks. We choose organic glass to make the mold because of 2 following advantages. This is the mold we designed. It contains 3 levels. Through this mold, we can produce gummy Lego bricks with exactly same shape and weight. This is the process of bricks production. Pour our solution into each gummy Lego mold and then cover the top level. After 10 minutes, solution gel was cooling completely. Then we can take out our gelatin bricks from each mold, then we got our bricks. These are 5 molds and 5 gummy bricks we've got. We use 15 of this mold we use 15 molds to produce the gummy Lego bricks as we need. Next part is about our measurement. We measure the elastic modulus of the bricks according to balloon test. We put the bricks on the platform and we use weight to provide pressure, and a traveling microscope is used to measure the deformation of the bricks. From the size of the bricks and the deformation can we calculate the elastic modulus of the bricks. Use collision method to measure the inherent frequency of the tower. Use a simple pendulum to hit the tower with a certain releasing height, and we use high-speed camera to record the vibration, thus obtain the inherent frequency of the tower. We use the electronic balance to measure the weight of the bricks. From the weight and the size can we calculate the density of the bricks. This is the result of all measurement and the theoretical prediction. The result of the experiment and the theory values are here. The maximum height of the tower becomes higher when the concentration of the gelatin bricks becomes higher as we see. The green line is the theoretical analysis and the blue line is the experimental result and the error range. We can see the theory coincide with the experiment result. Here is the summary. We found that the main excuse of the collapse is the vibration caused by external disturbance. We used Bernoulli-Euler beam mode to analyze it and found a relationship between the tower's height and the natural frequency, the elastic modulus, and the bricks density. We designed special modes to produce gummy Lego bricks and designed our 3 experiments. Finally, the experimental data coincide with the theory value within the error range. Here's our reference. And thank you for listening.
Thank you very much. The opposition on problem 3. Let us review the problem statement. So the problem statement asks us to build bricks, build towers with Lego gummy bricks, and specifically asks for the maximum height as it depends on the concentration of gelatin. And I believe the reporting team has focused on this part, and this is very good. But in the problem statement, there is also one other interpretation. What is the maximum height of gummy Lego bricks that can be built? They delimited the problem to one kind of tower, a rectangular tower. So in this interpretation, the problem was not fully answered. But I understand the delimitation. For an overview of the presentation, in the theory, they first analyze the ideal case and see it as a rigid body and a quasi-static process. And the investigate their hypothesis for a pre-experiment to see that the height is around 10 centimeters. And based on this, they develop a theory based on Euler-Bernoulli cantilever beams that are fixed at ground. This is the standard method to look at these beams, so this is a good approach. But they take it a step further than the simplest way to look at it, because they also look at the oscillations. We believe this is very good. For the experiments, they cast the Lego bricks in a pretty ingenious way. We are quite impressed. And they measure the elastic modulus through compression and the inherent frequency. To the elastic modulus, I may have some critiques, so we'll come back to that. And for the conclusion, they have a theoretical model that actually predicts the values, and they are quite close in agreement, but the error bars do not overlap for all data points. For the theory, the standard model is applied and extended because they include the oscillations. and there are numerical predictions made from theory. This is really good. For the cons, the tower is fixed at the base. This is not the only way to build the tower, so the theory could be extended to other cases quite easily, and we did not see that. And the experimental theoretical values are closely correlated, or they are quite closely correlated, but they don't match exactly, and we saw no comment as to why there is not a precise match. But I guess we'll come back to that in the discussion. We saw the failure mode bottling. There can be other failure modes as well, but there might be reasons why they are brought up. We'll see about that. For major cons, they ignore shear deformation. I believe shear deformation could be the key to make the theory and the experiments match precisely. And they also do the assumption that gelatin is elastic. This is not always true. It's true in some cases, and maybe we'll look into it if it applies in this particular case. For the experiments, they had a good casting process. They removed the foam, which is a thing that many people miss, because it introduces stochasticity into the problem, which isn't nice to have. And we saw measurements of the elastic modulus and the inherent frequency and the density. But are there limits to this theory? Could you dissolve an infinite amount of gelatin into the solution? Is there any part where the equations and reality don't match? This we didn't see. So for the discussion, I will talk about these points. Firstly, is actually gelatin elastic? And this is connected to my question about what is the relative compression level in the tower, and also during the measurements of the elastic modulus. And can you ignore shear deformation? Apparently you can get quite closely correlated theory and experiments, but maybe with shear deformation you can come closer. Also for the delimitations of the problem, could other towers get higher heights? And is there an effect of the interlocks? So I invite you to discussion. Have you looked into my previous question is what is the relative compression during your elastic modulus measurements?
You mean the dimension of the bricks when we measure the elastic modulus?
Yes.
It's about 1 millimeter. It's about 1 millimeter. The dimension of the bricks. You mean the variation on the height of the bricks, right?
Okay. So what is this distance? Is this distance 1 centimeter when we compress 1 millimeter when we compress it?
Yeah, it's about
9.6 millimeter.
9.6 millimeters. Okay. And what is the size of the whole brick?
The size of the whole bricks depends on the concentration of the gelatin.
But the height of the brick should be constant. It's just based on the mold.
It's a standard one, so
okay.
it's
so
9.6 millimeter.
It's 9.6 millimeters. But when you compress it in your test for the elastic modulus, how much do you compress it? How many millimeters do you compress it?
About 1 millimeter.
About 1
you mean the tower? Well, we have
no, just in the elastic modulus tests, 1 millimeter. Do you believe that gelatin is always elastic?
Because the mass of the gelatin bricks is very small, so when we build that, if the height of the tower is no more than 15 centimeters, it's okay. It's in the elastic force and the relationship between the elastic force and the dimension is a linear relationship. I mean, the Hooker's law is right. During
okay.
this, when the tower's height is no more than 50 centimeters, I'm sure that it.
I think that was a really good answer. I agree with you. But in this regime where the problem is that gelatin can be considered as elastic, but actually, in general, gelatin is hyperelastic. So it would be nice to have seen a comment on this, but I think your explanation was really good.
And you mean shared dimension?
Yeah.
Because we look at it ignore as well as shared dimension because the shared dimension is proportional to shared deformation is proportional to the deformation in the vertical direction, and we calculate it's no more than 1%, so we can ignore it. It's all right because it's no more than this number.
So you calculated the shared deformation for this?
Just not a precisely calculation, just emitted.
I didn't quite understand.
Because it's too small, really too small.
Okay, so where did you calculate what the shared deformation is?
Well, we first, could you give me this one?
Yeah.
Thank you. This is about the whole weight of the tower, and this is the gravity constant, and this is the elastic modulus, and this is the height of one brick, and this is the portion rate of bricks, and then this is this is the area of the bricks, and this is.
Maybe I'm not making myself clear. Is this the calculation of what the shared deformation is, or is this something else?
Is the deformation on the vertical direction, and the shared deformation will no more larger than this.
This one.
Yeah.
Okay. I think you've done really good calculation on this. My argument was based on that if you have the beam and it's bent, for shear deformation we have some kind of symmetry axis here. If we don't have any shear deformation, this angle is 90 degrees. But when I did the experiments, I saw that this angle is not at 90 degrees, that it's actually
maybe less or larger than that degree. I agree with you, but we calculate it because it's too small, so we ignore it and we consider the tower is bent. We use Bormio. We developed the Bormio-Ola model to describe the bend of the tower.
And it's of course not always.
As you can see, we consider it when it's bent, and this is of course analyzed, and we developed the standard model.
Keep us to the questions from the review. Thank you.
Thank you to the reporter for an excellent presentation, also to the opponent for raising some interesting questions about it. In review, we saw that the presentation was structured very simply. They presented a theory and that the disturbances are the main source of this tower's collapse, and supported that with the Bernoulli-Euler model. Next, they conducted a thorough experiment, which they supplied visual aids for to make it easier to understand, and their results agreed well with their initial predictions. The opponent, meanwhile, raised several questions about the experimental procedure, which shed light upon the process, and they also asked a few pertinent questions about the model itself. The reporter was particularly strong in their presentation and the easiness of understanding. It was easy to understand their methodology. The diagrams were large enough and easy to understand, and they offered a theory that matched well with their experimental results. In terms of weaknesses, though, the theory slides sometimes went too fast, and a lot of time was budgeted for the experiment itself. So I thought that understanding the results of their experiment were a little bit difficult in the context of such a short amount of time allocated to theory. We would have desired a plot with the varying concentrations of gelatin to help us understand exactly the relationship between concentration and tower strength. We noticed that there was also lacking discussion on both the part of the opposition and the reviewer and the reporter on how to optimize the tower's height, which is an important part of the problem and hopefully something we can touch on in ensuing discussion. The opponent, meanwhile, was clear and well-spoken, and they pointed out some oversights and suggested useful improvements. Again, though, I felt like we didn't touch enough on how to optimize the tower's height, which is also an important part of the original question. So I have several topics for discussion here, and I would like to first off see what you guys are most interested in discussing, but if possible I'd like to touch on further experiments that we could do to solidify and explain our results, and also other ways to optimize the tower, because I think it's most important to make the tallest tower according to this question. And there's several factors such as shape, base width, and manufacturing errors that we need to address in order to improve the height.
Okay.
All right. So first I'd like to address the reporter and ask, if you had more time, what is one experiment you would carry out to add to your results?
We thought the reason of the tower collapse is because of the oscillation. So if we want to try to do some research on the other structures, but if the tower is too large, I mean the basement of the tower is too large, then we need to consider when the electric wave inside the tower, when it do some oscillation vibrations. So we want to do some research on the elastic wave to do some research on the other structures.
So testing for Young's modulus. As for Sweden, if you could carry out one more experiment to add to this model, to this presentation, what would you carry out?
Okay. So China has presented the model. They have tested it for one kind of tower. So this model may work quite well for this tower, but the model also included the width of the base. You could easily vary the parameter of the width of the base to see if the model holds in more general conditions.
I see, thank you. Actually, that transitions well to optimization for the height. So I'd say, ask to the presenting team, how might you further optimize the tower? Address factors such as the base width, the tower shape, and the shapes of the Lego bricks themselves.
You mean the shape? I think the shape of the bricks is the standard. It's standard one because the problem side that it should be a legal brick. So I think the size of the bricks is the standard one. We can change the shape of the bricks, and you measure the shape of the tower, and as I think it's
because we found a problem on experiment is that when we produce when our production of the bricks finished, it will lose water very quick. So we need. So that's the reason why we use about 15 months to make bricks at a time, and that's the reason why we use this shape of tower.
Do you believe that the tower shape is optimal? That the height, that the tower's shape is the best possible shape for a maximal height of the tower?
I don't think so. Talking about the shape of the tower, we could test several even more shape. But we can't. What we need is to analyze concentration and the shape of the tower. We cannot analyze both of them in the same time. So what we need, if you're talking about the shape, what we need is to build a certain shape of tower in different calculation of the gelatin, and we can test if this theory could match with another shape.
I see. Thank you. Yes, I would like Sweden to speak to. Well, I'd like to have time for the opposing side to comment as well. So, would you like to speak to this?
Yes. I think China has done a good job with matching the theory to this kind of tower, and it would be really interesting to look at other kind of towers. Actually, in numerical simulations, you can show that the optimal tower, if you don't count for bricks as a continuous medium, looks something like this. So it's close to pyramid. So it would be really interesting if this theory could be improved upon to also include these kinds of towers, because it would make our understanding of the problem even better.
Great. I have a question from the audience.
So,
in the beginning of your presentation, you said that under ideal circumstances, the height of the tower would be infinite.
Yeah, but
You said that right?
yeah, but sure, it's ideal situation as I say. It never can achieve.
So is this really the case? Wouldn't the towers, say, crush under its own weight if you had an infinitely high tower?
The second point I said is a rigid body. It never collapses. The bricks it never collapse because of the weight.
Okay, but so
But there is the
the tower would collapse.
Yeah, but we calculated it because you can see the mass of the one brick is just several gram, and the elastic modulus is several k by s mean. If you want to make the bricks collapse, you need about more than 1,000 bricks on it. Then it will collapse.
So if you had a maybe you should keep the discussion on the state, but if you had a tower that there was absolutely no disturbances from the outside, would you be able to build a tower that was several thousand bricks high?
Several thousand?
Yeah, as you said you could.
Yeah, if there is really no external disturbance.
I can weigh in on that.
yes, would you mind speaking to it?
Yep. In this regime, we had buckling. For several thousand bricks, we had crushing, but somewhere in between, there could also be crack formation and add some gelatin by the moment. So that's one regime to keep in mind.
All right, so the opposition is about crack formation. Did you consider crack formation, and if so, how to affect the height of the tower?
I know what the author wants to say because if there is an external force and even there is no external disturbance, the tower will bend and then collapse. I know what the author wants to say, but this phenomena is strongly depends on the boundary condition and on our boundary condition that will not happen.
Excuse me. I think you're addressing crushing force. But the opposition mentioned that before the crushing force becomes significant according to your calculations, is it possible that crack formation and interface problems between the bricks would contribute to the tower's failure?
Could you explain detail?
Crack formation, for example, a crack to form right here.
There is a force.
Just manufacturing error, yes.
So what gives the tower this force?
Perhaps the opposition would like to expand.
Before the crushing actually happens, if we don't look at the bottom, we can have some small imperfection here, which makes this is a moment to fall. So there goes a crack, thus will probably happen down here. So I don't know if the judges see, so there can be formed a crack here, and then it will start falling.
You mean the bricks not connect very well, so there will be some...
Yeah, there are already connections between the bricks that aren't totally perfect, but there can also be new...
But remember, the brick is so soft and it is so sticky, and the surface of the brick is very sticky, so they will connect each other. And if under the external force, it will.
I have. Can we move on to another question now? I have a question. So you guys considered your process of building the bricks was very pure. You did a very good job. However, did you think about ways that manufacturing errors could still affect your tower, and how might we address those issues further? So manufacturing errors, such as some bubbles remaining in the tower, or just cracks forming at the interfaces. How might we minimize those effects?
I mean, as you say, the outer surface is so large, and if there is some the edge area is not perfect, it will influence very much. I thought, we thought it will influence so much because.
Okay. Time's up.
You can make
Okay.